sudden. Sorry for
because
that.
yeah,
Everybody gets shocked.
yeah, it is because of my sound here. I increased the volume, so I was so surprised because of your greetings.
All right. No
Okay.
worries about that. Hopefully that this just one time surprise and
Yeah,
no more surprise for later. But however, I just saw that somebody's just crying in here. If it's
yeah.
just crying because now
The course is not
sorry to
started. Yeah,
say,
the top,
yeah,
and
the
then
topic's
they pick
not
a
really
part.
friendly.
Yeah.
Usually we just get directly hands on writing some codes, but not for today. We will not open Visual Studio Code, so we are just gonna talk about the math, something
Yes.
that is kind of painstaking. But don't worry, at least here, Busiska will also accompany you to experience this headache together, right, Busiska?
Experience the headache. I don't know. Uh,
Headache. So the
okay.
headache, the headache. Yeah, right.
I know about the
Okay.
headache. Okay.
So the topic will be about the geometry, scalar, vector space, point, affine space, line, plane, frame, coordinate system, representation, dimension, and homogeneous coordinate. And this is going to be very important, especially for you to understand the nature of graphics rendering. So to know what what's behind the engine, the graphics engine that we have used so far, the WebGL, the OpenGL, or any other graphics library, they actually make use of this linear algebra to complete the rendering pipeline. And the good news is you only need to learn about this matter, this linear algebra, only to understand their nature. You do not need necessarily to understand these topics for helping you arranging or designing your algorithm, your solution for your computer graphics application. Because most of the linear algebra will be covered already, has been covered already by the library, so it's just kind of take for granted. The only thing that's you may get as a result of having us in today's lesson, having Busiska and me discussing about this topic in today's lesson, is simply to again understand the nature of the computer graphics. So you won't think that these computer graphics as some magic anymore. There is some logic even. So there's some mathematics, something that we can pursue to explore if you want, and that's not something that is magical. Oh, many more. I saw more kittens and cat pictures all over the chat channel. I'm so sorry that this picture won't appear on on the stream because my stream is only can only show the text, I believe. Yeah. No worries. You can check on the text channel on Discord to enjoy the picture posted by your friends. Anyway, for the slide presentation, as an alternative to open that using your Discord streaming service, maybe you want to save your bandwidth, you can also go to classpoint.app as always. So https classpoint.app/join, and then enter. Oh, today's code is just like McDonald's code. Almost the same. 14015.
Maybe yeah, maybe most of our students did not have a lunch. Maybe they
Yeah.
can open channel
Sorry,
because
sorry to hear that.
yeah.
I just got my boba here. This is
Oh,
my lunch.
boba. Oh, your lunch is boba.
It's sweet already. There are a lot of calorie.
Yeah, that's right. Are you on diet, Mr. Hazik?
Yeah,
Diet?
kind of. I need to go for diet because you know uh I'm become more and more chubby in this pandemic.
Yeah, many people.
Oh,
My weight increased into 10, 10
10 kilo?
kilograms. Yes.
Are you kidding me?
No,
Wow,
that's right.
that's a lot. Yeah, I've never
Yeah,
seen you
maybe.
quite a while. Yeah,
Yeah.
maybe I'm gonna very surprised when we meet each other later in the
Yeah.
campus.
Maybe you will not know me.
10 kilo.
I need to introduce myself when we meet after the pandemic.
All right. Actually, I also maybe gain 6, not up to 10, maybe just 6 to 8 kilo, but it's a lot already. I'm just kind of felt heavy with my own body. Okay, so the slide progress is in the meeting chat. You can have a check in there. Classpoint.app/join and then enter the 14015. Okay, the topic is about geometry. So we will have geometry in general in this slide, which is basically about the relationship between the objects in any dimensional space in an n dimensional space. So it can be any number. So when we talk about geometry, it's not limited to the things like we have already known, just like the shapes, just like the polygon or the cube, the sphere, something like that, something that we can visualize. It's not limited to that, but it is also something that beyond our imagination, it can sit or live in the higher dimension. For example, in fourth, fifth, or sixth dimension, is some higher level of dimension that we cannot possibly imagine. So that's geometry. However, in the previous meeting, while writing our code, our concern is mostly about 2D geometry. So we still kind of only care about x and y, so two properties of vector. And those vectors that we have defined in our code are basically in two-dimensional space, which means that our discussion was limited in the 2D geometry. So again, geometry is a relationship between objects in n-dimensional space. If we talk about 2D geometry, then it will go specifically to the relationship between the objects. The object in this case means that's collection of vertices that we have, or maybe the pictures that you have taken and submitted to your repository for assignment number 1. The looks of those pictures that is basically on the flat screen is a 2D objects. It sits on the two-dimensional space. However, even though we only cover two-dimensional space, only cover 2D geometry in the previous hands-on, later in the computer graphics we will cover the geometry in general is in 3D, okay, in three-dimensional space. And actually the one that we have implemented, we have manifested in the previous meeting, even though it's a two-dimensional, but actually we put it in a rendering pipeline that actually works for 3D geometry. Okay. So specifically in computer graphics, later we are interested in studying relationship between objects in three-dimensional space. Most of the time, we will manipulate the objects in this three-dimensional in the three-dimensional space as a S3D geometry. All right. Now to start our discussion about the linear algebra, that was just the beginning. I mean, it's kind of not even introduction. So when we talk about the linear algebra, about this 3D geometry, we need to review back our understanding in a linear algebra back then, starting with the scalar. Okay, scalar. This is a very easy concept. So let's start with the easy one, so you won't get any headache for the next slides. Please do remember that scalar in here is a very simple. It's basically just a number, represent some number that can be a real number or complex number. It can be both of them. It can be either the real or the complex number system. Do you still remember what is the complex number system? Maybe I need to remind you with this. Let me go. Okay. Complex number system is basically something that goes I think something like this, right? So this is complex number. This is just like a number. AB is a regular number. For example, 3 plus 2i, okay? And this I is the characteristic or something that is introduced as specifically for the complex number system. Yes, exactly, Fitra, you are right. So I is, I'm sorry, got some problem with my tablet. Okay, over here.
I'm sorry, Mr. Hazik, for interrupt your presentation. You do not share your screen.
Pardon? Really?
Yeah, you not share your screen.
Oh yeah, I'm so sorry.
Yeah.
But actually, the class point works the same. Oh yeah,
but
it's
cannot
already.
join to the class point. Maybe the
Yeah. We only have 25. Thank you very much, Busis. I just didn't realize that. I'm so sorry. So, okay. Okay. I equal to Imam. How did you? Why did you say that the complex number is the most selfish number system? This is quite interesting statement from you.
Because there is a lot of I in it and not a lot of we, you know.
Okay. Okay, nice joke. So I is actually -1 as the square root of -1. And later, actually you will get a better understanding later when I teach you about quaternion later. You will need to understand complex number first. Just give you some briefing information or some brief introduction to the why it's the logic behind the I number. So suppose that you have this Cartesian, and then you have a y-axis and x-axis, for example, and then I is kind of in linear algebra, we represent I as a 1/4 rotation. Wait, give a moment. Yes, 1/4 rotation in this Cartesian. So for example, if you go from this point, this is 1. Okay, for example, you go 1/4 rotate. I'm sorry about this. You rotate 90 degree counterclockwise, and you will find this I. Okay, And then when you give me a moment. Minus. Yeah, and when you rotate once again, you will arrive at -1. Okay. That's why I square is equal to -1. So you go with I first, and then you go twice. One fourth rotation mean the multiplication of I itself. So 1 multiplied by I is on the spot, and then when you multiply it by I again, you will go to -1. And then when you go multiply -1 with I, then you go to -I. And if you go once again, the fourth step, then you go back to 1. Okay, so in this case, you can say if you go fourth time, this factor of 4 in here, then you may find that the result will be 1. So this is the basic idea of I, and we will dig deep about that later when we learn about the quaternion, because quaternion is something to do with the rotation as well. Okay, so back to the topic of scalar. Awesome, thank you, Gary. I will check it out later. Thank you so much. Okay, and when we talk about scalar, basically the scalar should satisfy these two operations. So we should be able to operate two scalars with addition and multiplication. This is the direct operation. Indirectly, since we can do addition, so indirectly we can also do some subtractions, because subtraction is basically addition with the negative numbers. And if we talk about multiplication, indirectly we can also operate the division, because division is basically multiplication with the inverse of that scalar. It's not inverse. Yeah, it's not inverse. I'm sorry. So it's kind of one over scalar, some scalars that number. So that means that any scalar should satisfy addition, subtraction, multiplication, and division, and which obey the basic axioms: associative, commutative, and inverse. Hopefully, you still remember this. I will not go into the detail about this. You should have a check on your notes back then on your senior or junior high school. I believe that you have learned this. Sifat asosiatif, sifat komutatif pada penjumlahan, pada perkalian, dan sebagainya. Inverse means just simply give the negative signs to your number, to your scalar. And this is very important to understand that scalars have no geometric properties. The only thing that will have geometric properties is the next one, which is vector. Okay, in vector, maybe I need to hide out my picture. So in vector, we basically not only talk about the number or the magnitude, but also we need to speak about the direction. So there are two attributes that we need to take up to care about. The magnitude, in bahasa we call it besaran, okay, besaran dan arah, magnitude and direction. Some examples include gaya, force in physics, and also you also learn velocity in physics. Okay, velocity is kecepatan. There is other besaran that you may still remember. Laju, which means in English is speed, is something that has magnitude but doesn't have direction. So for velocity, it has some direction. Speed does not. Okay, it's just a matter of term actually, but you need to remember that in case that you need to defer that. Okay, force, velocity, and this is the thing that we will use continuously in this computer graphics course. Directional line segment. This is the most important example with respect to graphics, and we will use it all the time when we talk about the computer graphics. And then to these vectors, we can do several things. We can operate the vectors with several things. For example, set it an inverse, and actually every vector should has an inverse, always has an inverse. V, the inverse of V is negative V, and it will goes to the opposite direction with the same magnitude. And then any vector can be multiplied by a scalar. So alpha in this case is the scalar, and V is the vector. This arrow represents the vector V, and the alpha is the vector that will be multiplied to the vector that we have. And there's a possibility that we will find what's so-called null vector or zero vector whose orientation is undefined. If we have some magnitude that larger than 0, it's easy to notice. It's possible to notice that it has some direction to some particular way. But if that's 0, then maybe it brings up some question. Then in which direction the null vector or zero vectors heading to, the answer is undefined. So this is a very unique characteristic of the null vector or zero vector. And then if you add two vectors, sum the two vectors, the result will be also a vector. For example, in here you have a vector u and vector w. You add up these two together, then you will have v vector as the resultant of the vector. Okay, before I move to the vector space, maybe I need you to explain this as well. That in physics, perhaps that the representation. So we may have a physics. The representation of vector is usually using arrow, just like the one that we have just learned now. In mathematics, usually they will just represent that with some numbers, and just like what is written by Eve. So perhaps it's gonna be something like this. So we represent it this way. So it's in math, and perhaps in another way, just like matrix. For example, something like this. This is in math. And also this is behave the same with just what we learn in computer science. Okay. We usually will define some array. So we will just like in JavaScript that when we define the vertices during our hands-on, so we have this array, and these arrays actually just a matter of transpose comparing to the one that we have in mathematics. And back then when we learn this vector in linear algebra, may you remind me, could you please remind me in which semester you took the linear algebra?
I think it's the third semester.
First? Fourth? Fourth. Four. Okay. Am I right, Fred? I'm sorry because your microphone is kind of...
Third, I think. Third. Ketiga.
Oh, I'm sorry. Okay, thank you. Third semester. So that's 1 year ago. Okay. So usually in math or in linear algebra, we will use column to represent the vector. In computer graphics, it's impossible for us to draw in column, so we would just usually declare it in array. Your array is just a matter of a row, actually. And the keyword that we need to just remember is just basically the factor in computer science, just a matter of list actually. It's a list. So this is the keyword. So there's some question from Evelyn. Do we use vector inverse to create the mirror side of our shape? Yeah, that's one of the strategy. And this is very, very good question. And it reminds me to the nature of vector. If you suppose that you have a, for example, maybe I will need to draw in a whiteboard. So let's say that in your vertices you have 1 point. You have 1 point, for example, let's use yours, 3, 4. So this is the X, this is the Y. Okay. Maybe I need to appear on the screen so that you can also check your question in here. Okay, so this point or this vector, actually this is a point because we want to draw a vertex in our canvas. But let's say that this is, so for now it's a vector, okay? This one vector, so if I draw it in Cartesian, so for example like this, and let's assume that this is 1 unit, okay, and I go upward something like this, it means that 3, 4 is about this way, right? Okay, now let's say that we call this particular vector as V, okay? If we want to make it like, for example, I'm sorry if the scale is not really correct. Let's see, this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, at least this is approximately like this. So 1, 2, 3, 5, 4, 4, 5, 6. So I say that this second V apostrophe or V accent is basically 2V, right? And here is the scalar. We have V as a vector and we have scalar. Now you understand, it's kind of like a spoiler. This scalar is kind of something that I think I need to hide the, maybe I need to move to the another. I'm so sorry. Oh, it's hidden. It's hidden. Okay, over here. So something that can resize. I'm sorry. Yeah, resize. Yeah, okay, resize or scale the vector, right? Here we go. We have something that can resize or scale. So it is derived from the word scale. So in English, scale is a verb and scalar is the kind of the subject that can scale something. That's why it's called scalar. In bahasa it goes to scalar, something that maybe kind of sesuatu yang bisa memberikan skala kepada vektor. So that's the origin of this word. And as you might wonder, if we have this scalar negative, for example minus 2V, okay, then basically we will need to go to the opposite direction, okay, and that might be also part of your concern. So we kind of got the mirrored version of this vector. So if you give that V, or maybe you only give the to be honest, if you want to have the exact mirror maybe towards this y-axis, then the scalar is not that simple. So we cannot use the simple scalar to represent this new vector. We need to use some other type of transformation that we will learn in the next week meeting. Okay. So hopefully this will also help you to understand the nature of scalar and the vector. Now let's move to the next slide. Talking about more complex thing, linear vector space. In Bahasa, previously maybe you have heard this as a ruang vector. Okay, as ruang vector. And I may put this linear inside a parenthesis, so we can just simply call it a vector space. Ruang vector or vector space is a mathematical system for manipulating vectors. Okay, just take it, grasp it for granted for now. And the possible operations on the linear vector space will be these two. And these two particular operation will be used all over the place when we talk about computer graphics, or about the linear algebra in general. Scalar multiplication and vector addition. You can add up two vectors or more and got some resultant or some results. And also you can also give some numbers to the vector v, multiply with that number, and you get some other results representing yet another vector. And as long as the equation is derived from these two possible operations, then it means that this equation resides in the same vector space. Perhaps you say that this equation is different with the one that we saw above, because the above part is kind of very simple. It's a single vector plus yet another single pure vector, and then the multiplication is just one. How to say that in English? In Bahasa usually we say that it's a suku bilangan. It's a suku bilangan. However, this is also actually satisfy these possible operations. We can perhaps in the fact on that discourse v is equal to 2w. We do not know, and maybe v is also the addition of a 2w with minus 3r. Perhaps. So if the v is actually the derivation of these two vector, then actually we can also represent this as this is just a vector addition. So no matter how many suku bilangan you put in here, as long as it's simply plus or minus, so we can say that this is basically some linear vector space. Something that sits or resides in linear vector space. All right. We move to the next one. Now, if we talk about, I need to go to the bottom left. So now vector has no position. Very important. Okay. Vector has no position. Vector has a direction, but has no position. It doesn't have position. On the right side, as the examples, we have three vectors. The magnitude is identical. The length, represented by its length, is identical. It's also heading towards the same direction. But in this case, we still, even though it's in the different place, we can still say that these three vectors are the same. Okay. Again, vector has no point if it has no position. If we want to represent any position, we need another terms that's called points. Okay. And this is something that goes in a different manner starting from now. So that's why in our code, we need to distinguish between the vector and points. If we want to draw it as something on the canvas, it should be point. Vector is kind of the representation of motion, so it will fit best for transformation, for representation of motion of some points, but it's not points in and of itself. Evelyn asked a question. So every time we want to draw a vector, it must have a point then. Good question, but I will not answer that now. The answer will be in the next slides. Bear with me, and you will get the answer later. So, after we learn about the scalar, about the vector space, now we need to learn about the points. Point is a location in space. And if the case is just like the one that we have in the computer graphics, everything that is represented by some vector, usually its tail, if we talk about some vector, it has some tail and tip, right? Head and tail. Its tail usually rooted in the origin 0.0, and its tip is appointed to some particular position. Now, in the end, we have a position. Later, you will learn that the prerequisites, the requirements to have a position is, in addition to vectors, you have to have an origin. So that's the key point. Gary asked a question. When I use Unity or 3JS, the point is represented as vector 3 object. Is there any reason for that? That's just to simplify the representation, because when we talk about the vertex, we will not clash it with we do not clash the vertex as a position with some other vectors discourse. So that's fine. But in the end, after we throw these data, this collection of points represented by a vector 3 object from the JavaScript or from the desktop client, from the application to the GPU, to the graphics realm, then you will realize that in the end, the graphics shader will treat the points and vector differently. And that goes to the help of the homogeneous coordinate. You will understand that after you learn that. Also in this course. Also in this session. So let's wait for that. There will be some explanation and the answer for your questions. So let me continue first. The operations allowed between points and vectors is something like this. So the first one is subtracting a point from another point. The result will be vector. The second one is adding a point with a vector. The result will be a point. And these two equations is actually linked all together. So we just relocate the variable. Okay, maybe some of you need some translation because this is a very heavy topic. So let me speak in bahasa now. So, jadi pertama tadi kita sudah belajar tentang skala ya. Skala itu tidak punya arah, dia hanya sekedar angka, dia hanya sekedar besaran. Kemudian kita dan gunanya skala ini untuk memperbesar, memperkecil, atau bisa jadi memperbalik arah dari sebuah vektor yang dia kalikan. Skala akan menjadi sebuah faktor pengali dari vektor. Itulah dia kenapa namanya skalar ya. Karena dia mengskala sesuatu, mengskala vektor dalam hal ini. Nah, vektor sebagai tambahan, selain punya besaran, dia juga punya arah. Dia punya arah sehingga kalau punya arah, nanti kalau misalkan dia dinegasikan, maka arahnya akan berbalik dan seterusnya. Nah, beberapa vektor itu bisa dikumpulkan dalam ruang vektor yang kemudian kita bisa lakukan operasi penjumlahan antar vektor dan operasi pengalian vektor tersebut dengan sebuah skala. Jadi 2 operasi itu ya. Terus selanjutnya tadi kita belajar tentang titik. Jadi setelah tadi skalar itu dia hanya angka, kemudian vektor itu adalah angka plus bilangan atau besaran plus bilangan, suatu yang punya magnitude and have some direction, tapi tidak punya posisi. Masuk yang lebih advance lagi namanya point. Nah, ini sekarang yang kita bahas. Point itu punya angka, punya besaran, punya arah, dan punya posisi. Bukan punya arah juga sebenarnya, dia lebih meng-embody ke lokasinya, lebih ke arah untuk representasi. Jadi derajatnya mestinya bisa kita bilang setara gitu dengan vektor. Jadi kalau vektor tuh punya arah tapi nggak punya posisi, kalau titik dia punya posisi tapi nggak punya arah. Dia merepresentasikan satu lokasi. Antara titik dan vektor itu dimungkinkan untuk dilakukan 2 operasi. Yang pertama pengurangan titik dengan titik itu menghasilkan vektor. Kalau sebuah titik ditambahkan dengan vektor akan menghasilkan titik yang lain. Kebayang ya? Gampang banget kok bayangnya. Coba bayangin pakai yang atas ini. Imagine that you have a point Q and point P. If you subtract a Q from P, then as a result you will have you will have a vector rooted from the Q heading towards the P and end up its tail. Its tip or its head on the P position. So this is the result of the subtraction of the Q from P. P. Additionally, you can get the P by adding Q with a vector V. Okay, and these 2 simple equation will be very useful to understand the next step. Okay, so please do remember this. Now, yet another thing. After we talk about vector space, now we learn about affine space. In vector space, basically you do not have origin. Ketika tadi kita bicara masalah ruang vektor yang di depan tadi ya, itu dia tidak punya titik acuan utama 0,0-nya gitu, anggaplah seperti itu. Nah, di affine space itu pada dasarnya hanya menambahkan poin aja, hanya menambahkan titik. Affine space adalah point plus vector space. Nanti ini akan sangat berguna untuk memahami yang the next step. Operasi-operasi yang memungkinkan pada affine space, addition of vectors, ini seperti yang kita punya di vector space ya. Terus multiplication of scalar with vectors, ini juga kita dapat dari vector space. And then addition of point with vectors. Point with vectors itu kita dapat barusan dari operasi point yang di slide sebelumnya, pas. Terus ada addition of scalars, ini juga kita bolehkan di affine space, terus sama multiplications of scalars. Perkalian skalar dan penambahan skalar ini boleh. Ini ekstranya. Yang ini dari point, yang ini dari vector space, yang 2 ini, yang atas. Terus kemudian ada kejadian khusus juga, misalkan di sini kalau kita lihat 1 multiply by P is equal to P, is a very acceptable, gampang dipahami. Nah sekarang 0 multiply by P, titik kalau dikalikan 0, ternyata itu hasilnya juga 0. Dan ini kita sebut sebagai null vector atau zero vector tadi. Jadi titik itu ketika dia jadi dikalikan dengan 0, if we multiply some point with 0, it can no longer point. We can treat it as vector when it is 0. Nah ini sifat yang kita manfaatkan untuk homogeneous coordinate. Nanti kita akan bawa ke sini. Sorry, saya ngedang-dangi ya. Saya tak metu ya. Okay, I'm sorry to block your view. Now, let's have yet the next step term. After learning about the points, now let's go with the line. what is the definition of line? Consider all the points of equation P, the function P with the parameter of alpha equal to P0 or PO plus alpha D. Now, imagine that this P is actually, we will use this as wait, give a moment. I think, yeah, this one is gonna be the line, representing the line. This one is representing the origin, and it's basically point, origin point, and this represent some vector, right? D is vector, alpha is some because basically vector is a motion. It represents some motion. This in this case is a vector. And then we would like to set all, and we will not set the alpha as some particular or specific number, but we just let it as alpha in this case. Set all points that pass through PO in the direction that the vector D has. Bayangkan Anda punya PO di sini, P0, kemudian set all points. Jadi bikin titik yang melewati yang mulai dari PO ke arah D. D itu yang biru muda ini. Kasih ya, semua ini dengan definisi alpha ini can be any number. Ya, can be any number in the real numbers. Sebagai hasilnya maka Anda akan dapatkan segmen garis yang tak terbatas ya. Itu definisi dari garis. Jadi definisi dari garis adalah P alpha ini dengan PO sebagai origin, kemudian ditambahkan sebuah vektor, kemudian kasih alpha. Alphanya ini all the real numbers. All the real numbers. So kalian harus mencobai semua. Bayangin kayak gitu. Mencobai semua bilangan real, ditembakkan, dikalikan dengan D. Nah, dengan demikian kalian akan langsung dapatkan semua titik-titik yang akhirnya nanti menggambar D ini. Menggambar P alpha ini. Dan itu yang kita sebut sebagai garis. Itu definisi garis ya. Dan ini yang digunakan, konsep ini yang digunakan juga nanti oleh GL lines, GL line loop, GL line strip untuk mengonsep apa sih sebenarnya garis itu. Mereka mendefinisikan garis, they define line as a collection of points from the origin of the defined vector and multiply by the any real numbers to that particular vector. Oke. Itu menariknya ya. Nah, dari yang definisi vektor yang barusan, sebenarnya kita aslinya itu memanfaatkan yang ketiga ini. Kita reflect back to the topic that maybe I believe you have learned this from the calculus. Calculus is something. Oh, I think it's not calculus in your curriculum. It's mathematics, right? Am I right? When I was in undergraduate, it's called calculus. I'm not quite sure in your case. I think it's another term. Yeah, say that. It's mathematics, right? May I confirm? Guys, are you sleeping?
Yeah, it's mathematics.
Pardon?
It's mathematics.
Correct. Good. Thank you for your confirmation. So in mathematics, I think mathematics 2. In your second semester, you have taught about the explicit and implicit representation of line, and I think this is the first one that you have received as lessons. So in this explicit representation, we interpret the gradient as the gradient of the line, and then we have h is the the y value in the y-axis where the line is intersect with. Jadi di explicit representasi eksplisit ini tentunya teman-teman masih ingat ya. Kita menggunakan M sebagai derajat kemiringan, kemudian H ini titik potong dengan sumbu Y. This is the explicit representation of line. And in the implicit, you just need to move the whole variables to one side and then remain the zero on the other sides, something like this. This is the implicit one. And usually it's very useful if the case was you need to combine 2 or 3 or more polynomials. So it's kind of combining several lines, for example, or have some linear, what is that, linear problem solving? I'm not quite sure what is the exact term for that. In bahasa, I remember that beberapa permasalahan bisa diselesaikan dengan sistem persamaan linear, right? So linear equation system, I believe. And usually you will need to put it this way to make sure that you can get the answer for the, I don't know, you want to look for the A or the B or the C in that case. But for the computer graphics, the most useful one, the most helpful representation would be parametric. Even though it's kind of looks like more complex, because to represent, for example, in the 2-dimension, you need to specify these 2 lines, all of them. So you cannot have just simply one line representation, just like the explicit or the implicit one. So you need to have a x alpha, and then alpha with x1 plus alpha minus alpha, and then the xo. And this is just to represent one dimension. Another dimension, if the case you want to have in something on plane or on surface on the 2-dimensional plane, then you will need the second line of parametric functions or equation. You will utilize y, for example, in this case, and then have the same alpha or maybe beta. I think it can be another letter, the Greek letter, etc. So this is the way you represent the parametric. The parametric representation of a line is more reliable because it can be expanded into curves and surfaces. If the case is just something like this and it's going to be linear, the representation of the object will be just a matter of a linear line. It's a stroke. In bahasa, it's just simply a garis lurus. However, you can also have some curve, hyperbolic line, basically non-linear linear representation of line using non-linear parametric functions. So you can modify this scalar for its vector that you have in the equation. Let's have a check on the next slide for more clear understanding. In the next slide, we have a ray and a line segment. Ray is in bahasa, we call it sinar. And the line segment is a segment garis. And in this case, the ray is kind of representing the vector. Okay. So suppose that we have, again in here, we have a Q and, not P now. So we have Q and R. Previously, we talked about this line, right? So it's something that infinite. It has no start and end point. So line, it's something infinite. But line segment, it always has some start and at the beginning and the end point or the finish point, the finishing point. In this case, we want to define some line segment. Then we need to have the origin. For example, this Q is as the origin, and then we should have a vector V, for example, in here, and then we should define as the. I'm so sorry for this. Yes, I'm sorry. So we can have the vector or points. So you can choose one vector 1 point or just 2 points. Because if we only have 2 points, actually it's very easy to get the vector, right? So you just need to subtract the q from r to get the vector from the previous equations. Hope you still remember from the previous slides. So it can be both ways. So you can choose between having 2 points or 1 point with 1 vector. Now, assume that we have this alpha will move not in a discrete way, but in more integral way from 0 to 1. So alpha should be bigger and equal to 0. Then P alpha as the equation that we will have in here as this line segment is P alpha is the line equation, is the ray sinar leaving P0, means in this case is Q, in the V direction. Okay, in the P direction. If you use 2 points, for example this Q and R, to define V, then P alpha, this is the equation or the symbol of line representing the line, the infinite line, is equal to Q, the starting point, plus alpha, and hopefully you still remember that it can be D, right, in the previous equation, or in this case is V, is alpha multiplied by V. Okay, so this is the initial form. And then we derive the V as R Q subtracted from R, or R minus Q. This is the same. It's actually also Q, also V. And after we have this Q plus alpha, and then put it inside this parenthesis R minus Q, we can we can take this alpha R out from the parenthesis and put it on the left one. On the left side, something like this, and then in addition to that, we can put this Q into the parenthesis, or maybe just simply put it this way. I will need to have it maybe this is to help you. Where's the mic? Oh, over here. Just do not know where's the location of my pointer. Okay, over here. So says that the Q plus alpha R minus Q is actually something like this, right? Minus alpha Q. You can shift this alpha R to the front and then put this Q on the right side of the alpha R, and you have this. So in other term, you can also write it this way. Okay, so this is and actually this is the parametric format. Okay, this is the parametric format. So it's, in the end, you can have this P alpha as the alpha R is 1 point. With this is another, and this one is a vector or point in this matter. And this is a vector, or maybe just call it. I'm sorry. It just let's call it just. I'm sorry. I think I won't. I should not mislead you. So let's just type it as point in this case. This is scalar. This is a point. Okay. So we have this alpha. P alpha as the parametric function. So basically this function will work perfectly to represent the line. So you can use this function to represent an infinite line. Now, if you want to have this function to help you draw a line segment, means some finite segment, then you just need to specify that the alpha should be between 0 and 1. Okay, the alpha should be between 0 and 1. Then you can get all the points on the line segment joining or connecting R and Q. So that's the simple solution for having a line segment from 2 points that you got. in the coordinate system. Now let's move to the next one. And this is just an additional topic. We will not dig deep into that for now. If we want to have a curve or surface in your drawing, then actually you can also work with that by defining some parametric function, but non-linear. The only difference is it's not going to be linear. So it's a non-linear function. And if you want to specify some non-linear function for the surface will live or exist in a 3-dimension, I believe, then you will need a second parameter. So in addition to alpha, you will also need a beta in this case. And this is to represent plane. For example, you can have a R. I'm sorry, it can also be in the 2-dimension, I think. So it's not only in the 3-dimension plane, it can also exist in 2-dimension, of course. But if you want to specify a plane, you need to have a beta as a second parameter. Only alpha will not suffice the needs, so you need the second parameter. For example, you want to have a plane P alpha beta, these functions, and you can start with this origin R, and then you have 2 vector in this case, U and V. You will have alpha as the scalar for the U and beta as the scalar for V. And then, as you might see in here, you can define the plane as a point with 2 vectors, an origin with 2 vectors, or 3 points, just like the example on the right side. We just need to derive the function, the equation, by modifying or transform this U into Q minus R, okay, and V into P minus R. So this is what we got, and extract out the whole variables, the whole suku bilangan, and then we got this, and then we collect the same scale, the same point at the same suku bilangan. Then we got R. We have 3 R in here, right? And can put this I1 minus alpha minus beta into this parenthesis to be this scalar for R. And then we have alpha Q and beta P. So this is the equation for plane. Now, yet another affine. Back then we have a affine space. Now we have affine sum. What is affine sum? Let's say that we have a sum of P equal to alpha 1 multiplied by P1 alpha 2 P2 plus blah 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 up to alpha n Pn. Using induction, we can demonstrate that this sum makes sense if and only if alpha 1 plus alpha 2 up to alpha n is equal to 1. In which, in this case, we have an affine sum of points P1, P2, up to Pn. In addition, if alpha I is more than or equal to 0, then we have a convex hull of points. Saya pakai bahasa Indonesia ya. Jadi misalkan asumsikan kita punya penjumlahan dari setiap kita punya P ya. Kita punya P. Kita mau definisikan P. P itu apa? P itu kita punya beberapa titik. Titiknya bisa ditempatkan di mana saja di ruang vektor, in the vector space. Kemudian kita kalikan dia dengan sebuah alfa, ya. Sebuah alfa. Nah, alfanya itu seperti yang saya bilang sebelumnya, it can be any number in the real numbers system. But in this case, we want to specify that the alpha one should be more than or equal to 0 supaya kita bisa mendapatkan yang namanya convex hull. Sebuah kumpulan titik yang dia itu bisa mencakup titik lainnya. Jadi ini sangat penting terutama untuk konsepnya. Kalau tadi kan kita membicarakan masalah pembentukan garis ya. Jadi kita merasterize 2 poin, kemudian menyimpulkan bahwasanya namanya garis itu adalah kumpulan kumpulan titik-titik yang ada di antara 2 poin tersebut. Nah, affine sum ini ingin mengintroduce konsep yang lebih generik. Ini bisa digunakan untuk garis tentunya, sama halnya dengan yang tadi. Kalau misalkan kita isikan alpha 1 ini dengan any numbers from 0 to, pokoknya nggak boleh minus lah ya, 0 to some points. 1 usually, if we can make it 1, and then we can ensure that in addition to line, ketika di samping kita bisa mendefinisikan garis, kita juga bisa mendefinisikan bidang dengan menggunakan persamaan ini. Dan ini yang juga akhirnya dimanfaatkan oleh triangles, kemudian triangle strip sama triangle fan, konsep yang sama. Jadi proses rasterization yang ada di graphic shaders itu memanfaatkan konsep affine sum ini. Dan ini baru make sense kalau ini di total itu, jadi nggak boleh nggak boleh lebih dari 1 dan harus lebih dari 0. Jadi nggak boleh ini ada yang negatif juga. Misalkan alpha 1 dibikin 0,5, 0,25, terus nambah alpha 3 0,25 kan habis tuh ya. Terus ada alpha 4 0,25 lagi, jadinya 1,25 dikurangi ada something in the end minus 0,25, itu nggak boleh ada minus. Nah itu nanti kalau misalkan itu sudah terkumpul, maka dia akan bisa membentuk yang namanya affine sum. Kita cek secara praktikal di next slide. Ini convex hull. Convex hull itu the smallest convex object that covers all P1 up to Pn. Ini titik-titik P-nya ya. Titik-titik P-nya. Konsep ini penting terutama kalau misalkan nanti teman-teman perlu membuktikan apa ya? Clustering. Clustering ini juga kepake kalau ngobrolin masalah kecerdasan buatan, terus image processing dan sebagainya. Konsep convex hull ini salah satunya nanti akan dipakai juga di situ. Kalau di graphics kita bakal pakai ini salah satunya diantaranya untuk collision detection. Kadang ada beberapa objek itu kan dia nggak kotak sempurna atau bulat sempurna ya. Nah kalau misalkan mau dibikin serial mungkin object detectionnya, maka pakai konsep convex hull ini untuk membentuk. Jadi dari kumpulan vertex yang kita punya pada objek tertentu, itu kita akan specify area mana saja yang akhirnya menjadi batasan untuk collision detection. Terus ini definisi convexity. Spoiler alert, it will appear on your theoretical quiz. So you need to remember this. Ada yang namanya convex and not convex. Cara nandainya sederhana. Ini definisinya kalau mau baca secara formal yang ada di tengah ini. Saya kasih penjelasan secara praktikal aja. Jadi kita punya, katakanlah ada bentuk seperti ini, segi 5. Ini segi 6 ya. 1, 2, 3, 4, 5, 6. Segi 6. Segi 5 yang sebelah kiri ini yang orange dia convex. Kenapa? Karena kita pilih dua titik di area manapun di dalam area ini, di dalam area orange ini, itu selalu ketika kita hubungkan dua titik itu, garis yang terbentuk itu mengandung titik-titik yang semuanya titik-titiknya ada di dalam area tersebut. Nggak ada yang keluar dari area. Beda ceritanya sama yang not convex. Sebenarnya kita taruh titik sembarang ya, 2 titik sembarang di area yang abu-abu ini, akan ada satu momen, satu kondisi seperti yang ditampilkan seperti pada gambar ini. P kebetulan ada di sini dan Q ada di bawah sini. Kalau kita tarik garis, oh ternyata ada bagian titik-titik yang pada garis tersebut yang keluar dari bidang. Nah, ketika kondisi ini muncul sekali saja pada bidang ini, maka kita katakan dia not convex. Ya. Nah, ini secara lebih praktikalnya untuk bikin triangles, kemudian triangle fan, triangle strip, itu menyisir dengan cara yang tadi itu. Menyisir dengan cara si affine sum tadi. Dimulai dari affine sum yang garis dulu. Jadi antara P sama Q diberesin. Jadi alfanya itu harus antara 0 sampai 1. Kita harus punya definisi ini dulu, garis yang infinite di bawah. Terus kemudian dapatkan segmen yang ini dengan 0, alfanya 0 sampai 1 untuk vektor yang dibentuk oleh Q minus P. Oke, kita dapatkan semua titik-titik yang sini. Nah, tahap selanjutnya masuk ke iterasi nested loop-nya. Masuk ke iterasi yang berikutnya, level yang kedua. Ada titik yang lain yang R ini yang vektor bisa bentuk vektor dengan masing-masing titik yang tadi sudah di rasterize antara P sama Q. Nah, ini di nested loop-nya nanti akhirnya kan kita bisa bentuk di sini terus dia geser satu unit lagi, terserah nanti di sini. Makanya kalau if we still think about if we recall back our fragment shader source code, hopefully you still remember that we need to specify the resolution. It's not resolution, it's kind of the how precise is our float, right? So whether we want to use the medium P, high P, always remember that it's high P, then the number of segment that we will need to draw in this line segment will be more detailed. So you can imagine that. So semakin banyak semakin tinggi presisinya yang kita atur, maka itu akan menentukan seberapa banyak iterasi yang harus dilakukan oleh triangle formation ini. Jadi dia habis menyisir ini, dia akan menyisir ini. Oke, 1 sampai beres PQR-nya. Oke. Itu caranya. Terus ada lagi namanya barycentric coordinates. Kita bisa mendefinisikan koordinat. Jadi gini, misalkan titik yang sekarang ada di tengah ini bisa kita definisikan sebagai dua vektor ya mestinya sih, satu alfa 1 alfa 2 alfa 3 PQR berapa P berapa Q berapa R. Oh iya benar. Triangle is a convex. You can imagine the visualization from this particular slide, and then therefore each point in triangle can be represented as a affine sum. Each point in triangle can be represented in affine sum. Jadi kita bisa dapatkan definisi dari masing-masing titik yang ada di dalam segitiga ini melalui affine sum dari ini. P alpha 1, alpha 2, alpha 3 dengan alpha 1 itu dikalikan dengan P. Terus kemudian alpha 2 itu dikalikan dengan Q. Dengan Q ini. Alpha 3 dikalikan dengan R. Dan kita bisa letak, dan ini originnya tidak harus P. Originnya can be anywhere on the vector space. Misalkan di sini gitu ya. Maka kita tinggal taruh. Kalau kita mau mendefinisikan titik ini, maka pasti bisa didefinisikan dengan lokasi titik P ini dikalikan satu nilai alfa tertentu, alpha 1, terus dikalikan dengan Q2 berapa? Karena pada dasarnya kan P ini kan vektor ya, Q ini juga vektor. Selain dia sebagai titik, dia juga kalau misalkan dihadapkan dengan origin, dia akan menghasilkan sebuah vektor. Terus kalau vektor dikombinasikan, nanti kan dia akan bisa memberikan kita yang namanya barycentric coordinates ini. Coordinates di dalam segitiga yang didasarkan oleh vektor yang dipunya oleh masing-masing titik pembentuk segitiga itu. Nah, nanti kalau misalkan kita mau mendefinisikan titik yang ada di dalam segitiga ini, kalau kita total alfanya, alfa 1, 2, 3, 3-nya itu pasti sama dengan 1. Kalau dia nggak sama dengan 1, maka dia pasti di luar dari segitiga. Pasti di luar dari segitiga. Ini hukumnya. Terus alfa I harus lebih dari sama dengan 0, nggak boleh minus ya, nggak boleh minus. Oke, ini sebagai ilmu tambahan aja, dan ini kayaknya kepakai juga untuk. Tapi sekali lagi yang tadi saya sampaikan dari sejak awal sampai sekarang itu kita mostly take for granted. Kita sudah langsung pakai dari library-nya, dari graphics library-nya. Mereka yang menghandle untuk kita tinggal fokus ke bagaimana menangani vertex kita dan transformasinya bila diperlukan untuk animasi dan sebagainya. Terus nanti kita juga bakal butuh ini konsep normal vector. There's a spatial vector that we need to learn with respect to lighting and shading. We will use that for especially for that lighting and shading theory, lighting and shading topic. Okay. And the way we got the vector n, or this normal vector, is very simple. Basically, we just need to have any vector in this plane, any vector in this plane, and that's why in here you can 2-point in plane. Yeah, you can basically just pick any random point on the plane, and then we specify from that particular point to this origin what the resulting vector, and then get another point and what is the resulting vector. For example, we just simply use the this u and v vector, and then from this equation we will get that n. The cross product of these two vector is the n vector. Again, we will need to use this for lighting and shading later. All right, the next one. Or maybe let's have a break. Let's have a break because I think you are tired. You can have a drink first, or maybe you can leave some questions, and we will continue again at 2:30. Wah, coba kalau nggak pandemi ya. Mudah-mudahan nanti ada kesempatan gitu kita ada kelas offline, Rek. Tak traktir, Rek.
Amin.
Boba, Pak.
Boba wis karep merek apa wis.
GoFood, Pak, GoFood.
Iya, pakai GoFood nanti. Pesannya pakai GoFood. Ya kalau saya ngantri nanti nggak jadi kelas nanti.
Dosen mulu, Rek, disuruh ngantri.
Nggak jadi kelas nanti.
Ini kelas B juga ikut-ikutan minta traktir boba, Pak.
Ini kenapa ada kelas B nyasar ke sini?
Nanti kita buat kelas besar, Pak. Kelas A, B
Iya.
sampai F.
Aslinya nggak ngefek soalnya pakai Discord.
Iya.
Itu sudah ada spoil tapi dalam bentuk gambar ya, sayang sekali, bukan realita. Itu merek apa itu, If? Aduh, bikin pengen tuh kan. Nggak ada merek. Nggak di endorse. Tapi apapun merek boba yang ada di Indonesia itu nggak ada yang seenak yang saya dapat di Taiwan dulu. Emang originnya boba itu kan dari Taiwan ya.
Langsung kirim, Pak, dari Taiwan. Beli langsung yang banyak.
Iya, sayang sekali saya sudah lama nggak ke sana. Nggak ada jalan juga ke sana, susah. Harus nunggu postdoc. Kalau nggak gitu, kalau nunggu conference baru bisa bawa. Tapi keburu dingin ya. Itu resepnya kayak emang resep turun temurun ini nggak dibocorkan. Susah dapatnya.
Atau yang buat diculik, Pak, dibawa ke Indonesia. Boba di Indonesia.
Biji mana itu menculik orang bikin boba. Bisa aja sih. Iya, entah kenapa kok nggak ada orang Taiwan gitu kemudian dia pindah ke sini jualan di sini. Pasarnya kan gede ya. Gara-gara ngomongin boba yang naik level tuh. Singfu Tang, ya. Singfu Tang itu yang kayaknya paling terkenal ya. Ya, tetap aja masih belum ada yang sampai cocok seenak dulu yang waktu di sana.
Evelyn pernah ke Taiwan itu, Pak, karena tahu mereknya tuh sebutnya.
Iya. Oh. 你去过台湾吗 Evelyn 台湾哪里亚洲大学吗
就
比亚
怕
夏一是
是从中国，
树丛是台湾吗？不是大陆哦。
不是我的爷爷是从中国。
哦，是啊。那你讲话好像跟大陆人一样，台湾人讲话不是那样子。你是不是跟？
因为在我的家的时候，不是说福建话。
哦，懂，好懂。好了，大家不懂了，这样不好。Pakai bahasa manusia lagi. Ini bukan manusia yang tadi ya. Bahasa dewa.
lebih berat dari bahasa mesin, Pak.
Ya, itu bahasa Taifat. Bahasa Genshin Impact. Okay, let's continue our conversation about the linear algebra. now we are arrived at maybe Buziska, since you are joining with us, I need to use you as a benchmark. Did you understand with what I was explaining all along? I'm afraid that there's some parts that needs to be re-explained.
I think it's okay. I can understand it clearly.
Would you please help me to interrupt in case that you do not understand in any case? That will be very helpful for me, because if you feel that it's difficult to understand, then I'm afraid that the students will be more harder to understand my explanation. Thank you very much. Yeah.
Okay.
Now
Yeah.
let's talk about the linearly independent in bahasa. Back then, it was what was that? Bebas linear. Ada konsep namanya bebas linear di aljabar linear yang dulu. Nah, ini kita perlu cek kembali karena itu nanti juga penting. Linearly independent. The definition of linearly independent should be something like this. Suppose that you have a vector set v1, v2 up to vn. But in the case of computer graphics, I think we can stop at v3. I think v1, v2, v3 is linearly independent if the case is alpha 1 v1 plus alpha 2 v2 alpha 3 v3 is equal to 0, and only if alpha 1 equal alpha 2 equal alpha 3 equal to 0. Let me speak in bahasa. Himpunan, katakanlah kita punya sebuah himpunan vektor V1, V2, V3. Karena biasanya kalau dalam komputer graphics, dalam grafika komputer kita cuma stop sampai dimensi 3 aja udah cukup sebenarnya. Untuk definisi vertexnya. Itu kita katakan sebagai bebas linear. Syaratnya adalah persamaan yang ini, kanan atas ini. Tak sembunyi dulu. Persamaan yang atas ini akan bernilai 0 hanya ketika alfanya semuanya bernilai 0. Paham ya? Jadi ketika ada case alfa 1 atau alfa 2 atau alfa 3 tidak sama dengan 0, sekali lagi, ketika ada case alfa 1, alfa 2, alfa 3 tidak sama dengan 0, ternyata hasilnya di sini tetap 0, bisa menghasilkan 0, maka dia tidak bebas linear. Itu syaratnya. Syarat bebas linear nih harus terpenuhi dua ini. Oke, sebagai contoh ini. Atau mungkin tak bikin gambar baru lagi aja dah. Atau nggak usah deh, biar mempersingkat waktu ya. Saya masuk ke yang warna mana ya? Warna hitam ini dulu deh. Atau warna merah, warna hitam dulu aja deh. Warna hitam ini, let's say we have a set of vectors v1, v2, v3. And we put it as a column. So one vector, one column. This is just representation that we have learned from the linear algebra using column. Okay. But again, as I told you, in the end, you need to put this representation in aligned when we write it as a code in our program. V1, V2, and V3 have these elements. V1 is 1, 2, 3, V2 is 4, 5, 6, and V3 is 7, 8, 10. I'm sorry, this is my mistake. So 7, 8, 10. These vectors, in fact, are linearly independent. Mereka semua ini bebas linear. Mengapa? Karena syarat dari bebas linear yang lainnya adalah kita tidak bisa merepresentasikan satu vektor dengan vektor yang lainnya. Anda mau masukkan skalar berapapun, mau masukkan alfa berapapun ke V1, itu tidak akan bisa merepresentasikan V2 ataupun merepresentasikan V3. Lain halnya kalau misalkan saya bilang yang warna merah sekarang asum, mari kita bayangkan V1, V2, V3 sekarang 1, 2, 3, 2, 4, 6, 7, 8, 9 misalkan seperti itu. Di sini saya tinggal masukkan alfa bernilai 2. Oke. Kemudian saya jadikan pengali dari V1, maka saya bisa dapatkan V2. Ya. In fact, V2 is equal to V1 in this case. So I can represent the V2 with according to V1 with just one scalar. Okay. But in this case, V2 cannot be represented by V1 with just a single scalar. And also V2 is basically V1 plus V1. So basically if you can manage having all the vector from another vector by operating through the scalar multiplication or vector addition, then it's not linearly independent. Nah, kalau kita cek di sini nanti kita bisa buktikan V1, V2, V3 ketika kasusnya adalah 1, 2, 3, 2, 4, 6, 7, 8, 9, Anda masukkan ke sini, ke konvensi ini, maka dia tidak akan memenuhi. Tapi yang atas ini yang hitam bisa memenuhi. Ini kemarin saya tulis 9, saya pikir tidak memenuhi, ternyata ada masukan, kemudian siapa ya, Aldo kalau nggak salah dari kelas C ini nemukan, ini bisa V3 ini bisa direpresentasikan dengan 2V2 min V1. Dan it works. Jadi kalau 789 maka itu tidak bisa linearly independent, tidak bebas linear jadinya. Jadi pokoknya harus out of these two possible operations. Sekali aja satu vektor bisa direpresentasikan oleh vektor yang lain dengan menggunakan possible operations in vector space, maka itu tidak bebas linear. Pentingnya apa sih kita mengetahui hal ini? Itu untuk menyimpulkan bahwa saya sebenarnya kalau dia tidak bebas linear seperti yang ini, kita paksain hanya berdasarkan 3 vektor ini saja, kita tidak akan bisa mendapatkan sesuatu di dalam ruang 3 dimensi. Padahal harapannya kan kita ini 3 kali 3 ya. Ada 3 elemennya X, Y, Z, tapi kalau misalkan ada yang tidak bebas linear, akhirnya kita mentok ini hanya di 2 dimensi. Ini juga ada di 2 dimensi. Bayanginnya seperti apa? Suppose that, coba saya bikin sesuatu contoh yang lebih sederhana ya. Ini kenapa ya start menunya kok numpukin, sebentar. Saya ulang lagi. Why? The start taskbar is just blocked away. I need to hide this.
Maybe you can try to hide all the application by press the button right after the date time, and then you try. Ada tombol itu loh Pak, yang biasanya kan untuk meng-hide semuanya, semua aplikasi yang terbuka di pojok kanan bawah, terus nanti dibuka semua. Karena saya juga kadang nge-bug seperti ini.
Alright.
Nah,
Okay, got it.
then you can try to
not work.
Okay, I don't know. Maybe there's some bug in your monitor.
I'm just gonna hide this. Where's
Or
that?
maybe the computer is tired because many difficult things.
This one, it's okay. I can automatically hide it now. Just temporarily. So I can create. I just need to create new whiteboard. Okay, let's choose a simpler representation just in 2 dimension. Coba kita pakai contoh yang lebih sederhana aja, V2 dan V1 untuk 2 dimensi. Jadi kita punya X dan Y. Katakan seperti itu. Wait. Sebentar. Oke. Jadi kalau misalkan kita punya katakanlah 2, 3, dan 4. Yang gampang-gampang dulu aja ya, 4, 6. Maka teman-teman bisa bayangkan, misalkan kita punya definisi, langsung kita taruh di origin deh ya. Asum ini bisa jadi langsung jadi point. Kita bikinnya dari origin. Saya kasih unit. Dua, 3 itu berarti di sini vektornya ya. Ini adalah V1. Ini adalah V1. Kemudian 46. Kira-kira di sini. Kok rada gak tepat ya? Iki 2, 3. Oh, 46 di sini. Sorry. 46 sini. Nah, aslinya dia kan gini ya. Teman-teman bisa bayangkan di sini kan V2 itu equal to V1 kali 2 ya. Yang artinya misalkan teman-teman mau merepresentasikan, bisa nggak saya merepresentasikan titik di sini ya? 1 berapa nih? 6 atau ya misalkan 3,3 jangan deh, agak jauhan dikit. 3 misalkan 6,6. Bisa nggak saya tanya ke teman-teman semuanya? I ask you a question. If I suppose that why it's become okay. Let's see somewhere here. So you want can I utilize or can I make use of these two vectors to reach this point? The answer is impossible because these two vectors spanned only in this line. Okay, so this is one dimension. This is just matter of one dimension. But let's say that you have a V1 and V2. 2, 3, and for example 1, 1 maybe 1, 1. Then V2 is this one is the same, or maybe I'm just gonna write it down again. Draw it again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, approximately this is V2. I'm sorry, this is too small, I think. I'm so sorry. V2 and V1 is about here. This about here. Okay. So it spans in a different direction. Even though it's kind of hard, maybe, but it's still very possible to define. This is 1, 2, 3, 4, 5, 6 over here. So in this location, the same location, just like this, we cannot. We cannot find this. This is impossible. This is impossible to draw this using these two vectors. But it is very possible. But maybe the number that you may need to, or maybe not 6 by 6, because 6 by 6 is basically just 6 by 6 is equal 6 V2, right? Maybe we need to use another example. For example, 4, 1 maybe is over here. So let's say we have 4, 1. How to draw 4, 1 from these two vector? Can you help me? Let's say that I want to target this. This is the target. So let's say that I want to target this vector. So it's a 4, 1. How to represent this 4, 1 with this V2 and V1? It's hard, actually. It's hard, I know. You may need, but it's actually still possible to reach that one. And you may have some. This is gonna be alpha, and this is gonna be beta. The alpha will be kind of a decimal number. I'm so sorry. I blocked the view. So it's going to be a decimal number. And beta is also some decimal number, but it works. It will work. You will find this way because this V2 and V1 not sit in the... This is V1, I'm sorry. Not sit in the line, the same line. So it spans in 2 dimension. So these two vectors spans in 2 dimension. Okay, this only span in one dimension, and we cannot say that we will say that these two vector v1 and v2, the black one is linearly dependent. This is linearly dependent or not linearly independent. As simple as that. Linearly independent. Tidak bebas linear intinya ya. Tapi yang ini yang kita butuhkan. Kenapa menjadi penting nanti independent linearly independent ini independent linearly independent will be very important to make. So if these two vectors are linearly independent, then they can be used as a basis. Later you will understand this, the basis. This cannot be used as a basis. The black one cannot be used as a basis because they are not linearly independent. Maybe we need to move to the next slide so you will understand the function of what is linear independent and the basis. But before that, we need to grasp the concept of dimension. So in this case, for this one, these two vectors live in one dimension. Okay, live in one dimension actually. So wait. Let's read the exact definition first. The formal definition. In a vector space, the maximum number of vectors that are linearly independent is constant. This number is referred to as the dimensions of the space. In n-dimensional space, and linearly independent vectors from... the maximum number. So let's say that we have matrix 2 by 2, just like 2, 3, and 4, 6, and 2, 3, and 1, 1. We figure out that in this case, the black one, it can only reach the one dimension, the span is only one in one dimension, only one vector. There's no way to refer or to represent any vector out of this line for the case of the black representation. And as for the blue one, we learned that these two vectors help us to reach any points in this Cartesian system, in this coordinate system, in this vector space. Any points in this space is reached by these two vectors basically. And so that we call that we live in here is in two-dimensional spanning. Span in two dimension. So the answer for this system, the dimension of these two systems is basically 2 dimensions. Okay, 2 dimension. And for this is 3 dimension because the maximum number that's possible for this representation is 3, the maximum one. Okay. In an n-dimensional space, n-linearly independent vectors form the basis for the space. Jadi kalau misalkan kita ngobrolin yang 2 dimensi dulu deh, yang 2 kali 2 ini. Kalau misalkan kita temukan bahwasanya ada beberapa vektor, in fact kita setelah uji, ternyata mereka bisa independent linear, ya, bebas linear. Maka kita simpulkan bahwasanya V1 dan V2 yang bebas linear tadi itu dia bisa jadi basis. Ya, bisa jadi basis. Sementara ini yang V1, V2 dan V3 yang hitam ini yang bisa jadi basis, sementara yang merah ini hanya 2 yang bisa jadi basis, sisa satunya tidak bisa karena dia representasi dari vektor yang lain. Intinya seperti itu, apa yang disebut sebagai basis. Nah, ini supaya teman-teman juga tahu, saya perlu masuk ke whiteboard yang ketiga. Pada waktu kita belajar tentang Oke. Waktu kita belajar tentang Cartesian ya. Saya pakai warna hitam aja deh. Kita ingin merepresentasikan sebuah titik di Cartesian X sama Y aja deh. Yang paling simpel dulu. X sama Y. X dan Y sendiri ini sebenarnya adalah juga sebuah basis. Basisnya X sama Y-nya itu mana? Basisnya itu adalah vektor ini, vektor yang sampai ke unit 1 ini. Jadi kalau misalkan ini 1 unit ya, 2 unit, 3 unit, 4 unit, 5 unit. 1, 2, 3, 4. Misalkan seperti ini. Kita kan dapat ini ya. Ini kan 1, ini 1. Nah, biasanya kita akan merepresentasikannya kan kalau dalam format mathematics. Dalam format matematika ini kita bisa bilang ini I, ini J, ya. Sehingga kalau misalkan di definisi matriksnya itu atau vector space-nya itu adalah tadi itu 2, 3 dan 1, 1. Maka sebenarnya dalam representasi matematika ini vektor 1, ini vektor 2. Vektor 1 itu adalah 2i plus 3j. Ini persis seperti yang tadi ditulis sama if yang di bagian komen yang agak atas tadi yang pertama-pertama. V2 itu adalah i plus j. Kan gitu. Nah, ini sebenarnya ini basis. Ini basis ini. Ini sebenarnya juga vektor. Ini juga vektor i sama j ini. Ini adalah basis. Misalkan kita punya 3 vektor yang ketiga ya. Vektor yang ketiga katakanlah yang paling gampang dulu. I 2 3 2 3 I. Misalkan gini. Kita punya titik 34 ya. 3,4. Oke. Ini vektor yang di sini ya, vektor yang agak pencong. Vektor yang ketiga. V3 itu kita representasikan di sini kan berarti sebagai 3i plus 4j. Tapi aslinya kita juga bisa representasikan dia sebagai sebagai 1 VI ditambah dengan 1 V2. 1 VI kok 1 V. 1 V1 dengan 1 V2 ya kan? Kita kan bisa nyampe ke sini. Wait a minute. Is that? Yes, benar. Ya kan benar ya? Jadi kan 3 tambah 4 benar. 3 tambah 4. Kita bisa nyampe ke sini dengan definisi ini atau dengan definisi ini. Ini dua-duanya sah. Ini dua-duanya ini sah. Ini sah. Boleh-boleh aja. It's okay for us to define some vector according to one basis. One basis. This is Yes, this is a basis. Basis ij, or with another basis v1 and v2. V1 and v2 itself can be a basis. As long as the vector can represent the whole points in the Cartesian system, then it can be a basis. Jadi intinya seperti itu. Nah, nanti ini menjadi penting. Kenapa? Karena konsep transformasi yang akan kita kenal pekan mendatang itu sebenarnya hanyalah sekedar konsep perubahan basis. Ketika kita merubah objek dari berpindah gitu ya dari titik satu ke titik yang lain itu sebenarnya kita mengubah basisnya. Ketika kita merotasikan sebenarnya juga kita mengubah basisnya. Kita bisa melihatnya sebagai dari sudut pandang itu juga. Terus kita mau membuat efek perspektif itu juga sebenarnya kita mengubah basis dari dari vektor representasi vektor tersebut. Nah, nanti saya di akhir kuliah itu punya rekomendasi playlist yang saya sangat sarankan teman-teman untuk bisa pelajari supaya bisa lebih memahami tentang konsep vektor ini ya. Jadi ada tugas menonton. Tugas menonton dan tentunya tugas untuk menggambar seperti yang sudah diumumkan oleh asisten di channel kelas masing-masing. Okay, so that is the representation. This is very possible for us to represent one vector in many ways and in many possible bases. However, actually, up to now, we have worked with our geometry's entities without exclusively using frame or frame of references. We so far only use the coordinate system. The difference between frame and coordinate system is just like the affine space and the vector space. A frame of reference or frame require origin. Coordinate system does not. Okay, so for in this case, basically, if you want to play with the word coordinates, camera coordinates, you can forget or you can neglect the origin. Actually, if you want to move from one coordinates to another coordinates, but then later, if you want to specify something to draw on, you want to specify the points in which location it should be drawn, then you will need a frame of reference. This is the coordinate system. The requirement for coordinate system is basically a basis. You need to have a basis. If it's in 3 dimensions, then you need 3 vectors as the basis. And then you need to, all the vectors can be written in this format. And if it's the case for the 3 dimension, it should be alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. And then here we go. The representations of that particular vector, usually we do not necessarily to write down the v in our program. We just simply write down or type down the scalars. This A1, alpha 2, alpha 3 will be written as the value of our least variable that we have, and that's the representation. And it's basically in our case, most of the time in a computer graphics, we just simply use origin 0.0 and it's gonna be the word coordinate actually. So it's gonna be the word coordinates. As for the camera coordinates, perhaps we need to shift our origin later. And I will explain about that in the next week. We can write down the representation as a row or column. It's a choice. In a linear algebra, you can use. Usually, it's gonna be vertical, but in programming, there's no other way than writing the list in horizontal way. So we can assume that it's actually is the transpose of this part of this form. So this is just simply the one that I explained previously in the 2 dimensions. So you have this I, J, K, or actually you can also represent that as the vector X, vector Y, and vector Z, the unit vector of X, the unit vector of Y and Z. And so here we go. You can represent that as the collection of these scalars in column 3, 6, 7 or in row. This row representation in math, usually using this comma as a separator, but yeah, I think it's also the same for the case in our programming language. JavaScript array will need a comma to separate the value. Example of representation, so it's gonna be like this. The above representation is made on a certain basis. For example, in WebGL, we start representing vector based on the word coordinates using object basis, which means that we use 0.0.0 as our origin. But then the system needs to be represented in another coordinate system. For example, later we will need to transform to the camera coordinates, and we need to use another type of basis. But the representation, the representation will change accordingly. So it depends on the basis that we use. May I get your answer for this simple question? So, which one is considered as a coordinate system now? See, this is to review your understanding. Which one, left or right?
The left one.
The left one, I think.
The left one. Okay. The answer is both of them. Okay? Please do remember that we in coordinate system, we neglect or we do not care about the origin. The left one is specifically become more familiar to us because usually or most of the time we consider the vector that we have in the coordinate system are rooted from the origin, but it's not the case. Actually, it can be anywhere on the space. As long as this V can be represented by the collection of these bases, then it's fine. Okay, this V represented by the collection of bases. This is in particular is frame of reference. Okay. Again, coordinate system do not have a fixed location. If you want to have a fixed location for your system, it's called frame of reference. Okay, so we need to have a frames. Basically, frames is coordinate system. So collection of bases with origin. So that's the frames. The representation in a frame can be defined. I saw some questions in the chat from Gary. I will check it later. The frame is defined by PO, V1, V2, V3. So we have origin and we have some bases, V1, V2, V3. And in this frame, each vector, any vector in the space, in the vector space can be written as V equal to, this is the equation that we already learned from the previous slides. So each point can be written as, this is the point, an arbitrary point in the space is equal to the origin plus, this is the same equation, right? So it's basically origin plus this affine formula. Perhaps this start to make you confused. In fact, that in the JavaScript, usually we just treat these two things the same, vector and points the same. But in the end, our rendering library, our graphics library need to treat them differently. So in the case of having P and V with the same, for example, with the same magnitude and direction, but with the different but the case is for the V, it has no location, so it can be anywhere on the space, even though the magnitude and the direction is the same with the point. But so that's basically the difference. We want to represent this as just these three values, right? So this scalars, if it's possible that's gonna be the same, but how to differ them in case that our graphics library need to treat the vector and the points differently, because in fact vector will be used for transformation, for representing the motion, and the point will be for drawing something, for the vertex position, etc., to indicate some location to spot, some location to draw on the canvas, on the space. Okay, so this is the strategy. That's called homogeneous representation. Let's recall the equation that I have mentioned previously about the 0 multiplied by P by point is equal to 0, and 1 multiplied by P is equal to P. In this case, we can derive the formula into for example, if for this vector equation, if we want to put it just like in the matrix multiplication, if you still remember, this is matrix multiplication. So this is A, and this is some matrix M1, and this is another matrix that is transposed, means that this is in the form of column. Okay, imagine that this is a V1, V2, V3, and P0 in vertically. So you can multiply alpha 1 with V1, and this is the result, plus alpha 2 with V2, this is the result, plus alpha 3 with V3, and this is the result, and 0 with multiplied by P0. The results will be 0, right? And I said 0 vector is equal to 0 point. So basically it's nothing here. So we can just write it down as alpha 1 V1, alpha 2 V2, and alpha 3 V3 without any specification about the point. In other side, if we want to define some point, then we may need to have a different type of multiplication, matrix multiplication, beta 1 v1, beta 2 v3, beta 3 v3, and 1 with PO to ensure that we have the origin over here. And this is why we need to have this one number all the time in our GL underscore position. Because we want to specify that GL position is a point, not a vector. It has some position. It's not only about direction and magnitude. It has some position. So later, when we want to specify a vector in the end, even though it's a three-dimensional objects, we need to use four-dimensional representation instead. Okay. For vector, we just leave it as 0 for the fourth element, and for position or vertex position, for example, we should use a 1 in the end. And this is very useful for the shader later, especially you will realize that this is very important, especially when you have learned about the transformation. This one is just do its magic later. Okay. So here we go. This is the wrap up. This is the takeaway for today's course, for today's session. Homogeneous coordinate. This is basically the key to all computer graphic systems that we will learn throughout this course. All standard transformations, rotation, translation, scalation can be implemented by multiplying a 4x4 matrix. Later, when we want to rotate something, object in the 3 dimensions, we need to 4x4 matrix. The translation as well, 4x4 matrix. The scalation as well, 4x4 matrix. Yes, last week we animate our object in a simple way using a linear equation without any matrix. That's okay. We will try to compare them. So how to translate something using regular incrementation, just like last week approach, and using the 4x4 matrix. And we will realize that the 4x4 matrix is more powerful, especially if we want to combine various transformations for our object. If the case is just translation and only translation without any other form of transformations, then usually linear equation is sufficient. And that was the one that we approached for the last session in our hands-on. But later we will need to practice this because it's more powerful, it's more efficient and effective to transform any objects and vertex in three-dimensional space. And then we will later also need to learn about the two different perspective of view. Two different viewpoint. The first one is orthographic. For this case, we can use a vector 0, and this is the case for current. What we are currently doing, we are drawing in orthographic view. And I haven't yet told you about how to draw in 3D so far, because when we draw the 3D in our application, by now you cannot see the 3D effect. If you draw the cube, you cannot see the 3D effect because currently the viewpoint is still orthographic. It's just like the draw of architect students or architect engineers. I'm sorry, not architect. Architects are already something. It's not the architect engineer. Architects or maybe some some students of architecture. They draw the model. Usually they will use the orthographic approach to make sure that the size will not bias, will not blur. So they know the exact specification of their building. However, the way our eyes work, the way our brains perceive our surrounding is using perspective view. And in this case, later it's not going to be simply, the W is not going to be simply 1, just like in the homogeneous coordinate. We will need to do something, some yet another work of mathematics to transform the orthographic view into perspective view, the things that we usually perceive. Oke, saya sampaikan sekarang dalam bahasa Indonesia sebagai kesimpulan bahwasanya ini adalah inti dari pembahasan kita pada kali ini. Ini akan menjadi bahasan yang krusial untuk bisa memahami bagaimana shaders itu bekerja, bagaimana pustaka atau library dari computer graphics di GPU itu bekerja. Semuanya butuh koordinat homogen, yang mana dia perlu didefinisikan di dimensi keempat dengan angka 1 di belakangnya. Mudah-mudahan masih ingat dengan definisi GL_position ya, itu kan yang terakhirnya selalu 1. Alasannya adalah ada yang dijelaskan di slide ini. Dan homogeneous coordinate ini kan kelihatan semakin bermanfaat ketika kita bermain transformasi. Transformasi sekompleks apapun itu tetap bisa berjalan dengan sangat baik di komputer. Dan ini lebih baik bahkan untuk kasus yang translasi itu masih lebih baik menggunakan matriks 4x4 daripada hanya pendekatan linear, inkrementasi linear seperti yang sudah kita lakukan di pekan lalu. Nah, kita akan lihat contohnya nanti di pekan mendatang. Nah, sementara memang yang sudah kita lakukan belum kelihatan 3D karena kalau saya paksa teman-teman untuk bikin objek 3D-nya itu nggak akan kelihatan 3 dimensi karena masih menggunakan pendekatan ortografik yang artinya ya benar-benar nggak ada efek perspektif ya. Di efek perspektif yang kita harapkan itu kan ada kayak titik hilang ya. Objek yang semakin jauh dari mata akan semakin kelihatan lebih kecil. Terus ada yang kemarin saya bilang hidden surface removal itu. Objek yang ada di depan yang lebih dekat dengan mata akan menutupi objek di belakang dan sebagainya. Nanti kita akan pelajari untuk membuat perspektif ini kita butuh matriks lagi. There will be another matrix 4x4 matrix for this perspective view. Dan itu akan membuat kita semakin membantu si komputer untuk memberikan visualisasi yang memang kita inginkan sesuai dengan apa yang dipahami oleh otak kita ketika melihat sesuatu dari sekitar. And that's for today, and this is gonna be for your little homework. I think it's about 10 videos, 10 or 11 videos. And majority of what I was talking about in the linear algebra for computer graphics were taken from this video. It's a very useful video, very helpful and insightful. I believe that you can find it inspiring as well. Okay, before I end the session, maybe I can... Let me read this question from Gary. What if V1 equal to O1 plus 1J and V2? So the V3 can be... Wait, give a moment. V1 is 1J, V2 is 1I. Okay, so V3 can be 3V2. Yes, of course. So it means that your... Give me a moment, Gary. So what is actually the... So the V3 can be... In this case, actually, you just use your V1 equal to J, right? So your V1 is actually the basis of the y-axis. So V3 can be... The V3 can be 3V2 plus 4V1. Or maybe I'm just gonna need to go back to the slide though. I think you were talking about this, right? So let me go back to my screen. Were you talking about this, Gary? And for the Fitra question, I suggest you to read, I think, Gary's notes on the homework help. Okay, so it's very useful. Thank you, Gary, for sharing with us that OOP approach is, I believe, will accelerate the way you define the vectors. Okay. Gare, would you mind to confirm whether you have solved your own questions? I didn't find any problem actually on your questions.
Yes, sir. Yes. So I think only X or Y axis can be the base, but actually X and Y axis is the most common base. I think.
Yes, the most common.
Yeah.
Yes. And yeah. And it's like it's actually we can also say that it's a fabricated because even in our word we should define our own standard unit for measuring the distance, right, Gare? So you can have inch, you can have feet, you can have miles, but US people, US citizens will argue that I'm sorry, UK people will argue that sucks. We still need to use the metric, the international standard, etc. But for US people, they think that this is the most practical, the most applicable using the inch. This is up to them. So it's just a matter of basis. So you can also use your own custom basis. Even in here, it's just like you swap between the V1. You attribute the V1 to the vertical axis, and you attribute the V2 to the horizontal axis. It's okay. It's up to you, and it's very possible that it happens behind the scene, when you later transform your objects from one particular vertex position to another point. You will need to animate, you need to rotate. Usually that will happen later. Hopefully that give you a bit answer to your question, Gary.
Yes. Okay. Thank you.
All right. So this is a wrap, guys. So I will need to ask you together to have a pray. So hopefully that we can benefit a lot from this conversation. It's already 3:00 in the afternoon, right? So let me turn off the microphone. Okay, let's pray together. Okay, Alhamdulillah Rabbil Alamin. So we call it a day. Thank you very much for your attention. And we will see you again, inshallah, next week for linear algebra for transformation. Until then, good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Mr. Hazik.
Thank you all for having us.
Thank you, sir.